Okay, so for our warm-up today, we just have two functions, right, in function notation. F of x equals x squared plus 2x plus 3, and then g of x equals 7 divided by x plus 2. We're just going to evaluate some functions. Okay, so again, remember that when we look at a function, when I see the rule g of x equals 7 over x plus 2, that this tells us some information here, right? So in this case, g is the name of the function. Okay, and hopefully this is, in your notebooks, and we'll kind of start today's lesson with this warm-up. And then x is the input variable. And what that means is whenever we want to plug in some different number, like here we're going to do g of 2, we're going to remove all of the x's because the 2 will be there in place of the x. So we're going to remove this x, and in place of it we're going to put a 2. Right? So the x is just sort of the placeholder where we're going to put the variable, where we're going to put the input. And then g of x, or 7 over x plus 2, is the output of the function. That's the output of the function. So that gives us all that information there, and it lets us work with different functions throughout the same problem if we need to. So to evaluate these first couple here, f of 3 and g of 2, what we're doing there is we're just going to input for x, right? So here for f of 3, I'm going to write 3 squared plus 2 times 3 plus 3. I always like to put my input variable in a parenthesis. That really helps with distribution, or if you're squaring negatives, kind of help you avoid making some of those mistakes. So here at this point, we get 9 plus 6 plus 3. So that'd be 18. So then we have that f of 3 is 18. Right. And then you see this, that's actually telling us information too. For the function f, when you input a 3, you get an 18 as your output. So in terms of a graph, if we graph the function f of x, it would have the point 318 on that graph. So it means the same thing as an ordered pair, it just looks different. G of 2, so obviously we're going to go to the function called g of x. We're going to plug that in, and we get 7 over 2 plus 2, which is just 7/4. I would leave it as 7/4. That's, I think, the best way to write that answer. No decimal, don't need to make it a mixed number. Just go ahead and leave it as 7/4. All right, and then the next one here, they get a little, so these were just input a number, get a number back out. Here we're going to input a new expression. Okay, so for this first one, for f of x plus 2, we're going to go ahead and take the rule f. Wherever there's an x, we're going to replace it with x plus 2. Okay, so these get a little bit, we got to do a little bit of algebra here. So we get x plus 2 squared plus 2x, 2 parenthesis x plus 2, and then plus 3. Okay, so again, we took the original rule for f of x. It says take the input squared plus 2 times the input plus 3. So we took the input squared plus 2 times the input plus 3. Generally, you have to expand these here. We can't just leave it the way it is. Move this down. So what we'll do here is this is a binomial squared. So we'll take it, and we're going to, you could FOIL that out, or however you like to do that. X squared plus 4x plus 4 plus 2x plus 4 plus 3. Again, distributed the 2. Here, x plus 2 times x plus 2. And that's x to the 4th plus 6x plus 11. And that would be f of x plus 2. That would be a weird way to think of it, but even on that curve, if you graphed the function f, it would have the ordered pairs of the form x plus 2 would be all the input values, and all the outputs would have the form x squared plus 6x plus 11, or could have the form. Right? Could have that form. G of 3k. Well, here I'm just going to, again, I'm going to pull out the input variable, right, which is here, and replace it with 3k. So that gives us 7 over 3k plus 2. It can look strange. It's okay, but it kind of does. Okay, so here's where we're inputting another algebraic expression, right, to get that. And then lastly, hopefully you remember these are compositions of functions. So here you're going to take, if we're asked to do g of f of x is how we'll usually write that, you're going to take x and plug it into f, and then that's going to be your input. You're going to plug that input into g. So in this case, really just replace f of x with its function rule. So x squared plus 2x plus 3. Okay, so I took the f of x out, replaced it with the rule for f of x. Now g tells us 7 divided by the input plus 2. So here, to do this, I'm going to do 7 divided by the input, I'll leave that in a parenthesis, plus 2. Now at this point, there's no numbers touching the parenthesis that need to be distributed. There's no negative in front of it that needs to be distributed, so they can really just drop off. And we'll get 7 over x squared plus 2x plus 5, and that's g of f of x, like that. The last one here, which I guess I managed to half erase, is g of negative 1. And I don't know, when you first learned about compositions, there are really two ways you can write them. You can see them written like this, which we just did, or you see them like this with this little circle in here. It's not a time symbol, it's not a 0, it's not the letter O. It's just this little operator that just sits kind of midline there. Now it just means the same as g of negative 1. So whenever I see it, I usually just write it that way because this seems to make more sense to me. Start with the input and work yourself out. So the first thing we'll do here is we're going to put in negative 1 into the function called g. So that gives us, I'm going to leave the g on the outside, and then we get 7 over negative 1 plus 2. And we can all do negative 1 plus 2 is just 1. So that just gives you now g of 7. And then we're going to plug 7 back into g again, which the rule for g, remember, was 7 divided by the input plus 2. So we'll get 7 divided by the input plus 2. And that'll give us 7/9. So that's a composition, right? You take one function, you plug it into the other, you do all that stuff. Okay, so for section 1.2 here, the first thing we're going to start with is just recalling what a function is, right? So there's a lot of mathematical definitions, and I think sometimes they can get confusing, especially when you start to throw domain and range in there. So kind of the nice way to think about this is that each input, which is an x value normally, has exactly one output. So the biggest thing that we can think of with a function, kind of a fallback definition, is if I plug in any number into this function, I'm only going to get one answer. Right? If you ever plug it in and you get two possible answers, it's not a function, it's a relation. If we want to know the same thing is going to happen the same time we plug this in, the same thing in. We said we normally use f of x, or Euler's notation, which you don't need to know his name, it's just a mathematician that started at E-U-L-E-R-S, and it's pronounced Euler, which is kind of different. And then remember that the set of inputs we call the domain, right? And with that, that's the set of inputs. Those are the set of inputs that give us an answer, right? Like if you plug something in and you don't get an answer and you get undefined, well, it's not a part of your domain. You've got to be able to plug it in and give you an answer. So these are the x's which give a solution. Okay, and then the set of outputs we know is called the domain or the range. So part of what we'll look at today and throughout the week is if you have a particular function, what's its domain? Like what are the allowable numbers that we can plug into it to get an answer? And then the range is like what are all those answers going to look like? Right? Are they all going to be positive? Are they all going to be negative? Are they going to be numbers bigger than 5? Or whatever. That's what we'll look at there. Okay, so first couple examples here is just to try to tell if we have a function. So in this first example 1, we have some relation here. If you're not sure if it's a function or not, it's definitely a relation. It relates an x and a y together. Okay. So what we want to do is if you're not sure if you have something strange looking here, like we have an x squared, a y squared, here we have an x squared, an xy, is if you want to determine if it is a function or not, you just want to go ahead and try to solve for y. If you can get it to say y equals, and there's no plus or minus sign in it, then it should be a function. Now, I guess you could have some weird piecewise functions. You'd have to actually look at the graph. But so like in this case, do we know what this shape is? X squared plus y squared equals 16? If you remember from geometry, it's a circle with a radius of 4. That's the equation of a circle. Is it going to be a function? Hopefully you guys know it's not, right? But let's see how can we show that algebraically. So I'm going to try to solve for y. I'm going to subtract x squared from each side. And then I want to get y by itself, and right now it's being squared, so we square root both sides. And just thinking back to what we've done previously, whenever you're doing that and you decide to square root, you got to put a plus or minus sign. So we get y equals plus or minus the square root of 16 minus x squared. Again, if you have a plus or minus here, that's telling you it's not a function. So this is not a function. Now you actually only have to show that one time it happens where you get 2 solutions. So if you wanted to prove it here, you could say, well, put in the number 1 for x. Right? If I input the number 1, we get y is going to be plus or minus the square root of 15. Well, that's 2 different numbers, right? So that would mean that on that graph, you would have the point 1 radical 15, and then 1 negative radical 15. So it's not a function, right? There's a justification, because for this particular input of 1, we have 2 different outputs, not a function. Right? Each input has exactly 1 output if it's a function. For part B here, we have x squared plus xy minus 6 equals 0. So again, we have to solve for y. Now, it doesn't mean that we have to solve and it has to look nice. It just means we have to solve for y. So I'm going to say xy equals 6 minus x squared. Right, I just added 6 and subtracted x squared from both sides. And then if I want to get y by itself, we'll just divide by x. So we were able to solve for y. Now we can't reduce or anything here because of the minus. It's the way it is. But we can see that every time we plug in an x, we're going to get the same output, correct? So this is yes, it is a function. And then, let's see. The easiest way to tell something's a function, and this, you should have heard of this before, is called the vertical line test. Okay, and couple ways it can be written, but if no vertical line intersects the curve of f of x at more than one point, then f of x is a function. Okay, so we have our vertical line test. We just said if no vertical line, well, I guess I should have put line in there, huh? Intersects the curve of f of x at more than one point, then f of x is a function. Okay, so if we look at A here, we have a parabola that opens up. If we draw a bunch of different vertical lines, we ever going to hit it twice? No, even though it gets really, really steep out here, we know it's not good. It's not vertical, right? Functions don't have vertical pieces, so we don't expect that. So here we'd say yes, this is a function. Here we have same parabola laying on its side. Is that a function? No, it only takes one vertical line. So if I think of like the y-axis of a vertical line, correct? It has 2 points on that vertical line. It fails the vertical line test. It's not a function. And the reason being is you'd have a point 0, some positive number, right? Say 5. You'd have a point down here, 0, comma, some negative number. So that one input of 0 has 2 different outputs. So it's not a function. So that would be no. For C, here we have a piecewise function. Right, we can see there's a line segment, or I guess a ray here going to the left and to the right. Here we have an open circle. Here we have a closed circle. Now, if you draw a vertical line here, it is going to hit both of those points, correct? But since one of them's open, it's not actually a point, it's going to be a function. So this would be yes, it is a function. And lastly, another piecewise function, maybe half of a parabola here and some sort of ray. But if we look, here we have 2 closed circles, correct? So if we draw that vertical line, it's going to have 2 outputs. So on this graph, if it's called f, you said what's f of 0, you couldn't tell which one the answer is because they're both there. So this is no, this is not a function. Okay, so that's just a couple different ways to determine if we have a function. If it's an equation, see if you can isolate y without getting to a plus or minus. It's basically going to be the plus or minus part. It's going to be the difference. And then here we can use the vertical line test. Okay, so a lot of times we're going to have functions, and we're going to have to know what the domain is. We're going to have to know what x values have an output, right? So we want to figure out where it's undefined. Pretty much, if we're looking at a function, and especially if it's in the f of x equals or y equals form, there's really 4 things that we can look for that are going to cause domain restrictions. Okay, so 4 reasons the domain can be restricted, or domain is restricted, as it should be. So there are other reasons here, and a lot of times, one of the biggest ones is if you have a word problem, certain answers make sense and certain answers don't make sense. So that's part of it. But in terms of just the pure algebra, the 4 reasons that the domain will be restricted, the first is it causes, so it's going to be restricted if the input x causes one of these 4 reasons. Division by 0. If it causes you to divide by 0, that's a bad input, right? Dividing by 0 is not a thing that we do. We can look at some examples of that. The other thing is it has a negative under an even root. Right, so if it has you trying to take the square root of -16, even though we know there's imaginary numbers, in terms of domain, we're just talking about the real numbers, unless specified. Okay, so negative under an even root. And this also, just be careful. With rational exponents. Right? Because if you have a 1/2 power, that's actually a square root, correct? They can kind of hide there. If you have a 3/2 power, it's cubed, but it's still getting square rooted, or a 1/4 power, things like that. These are the 2 that we're going to come across here initially. By the end of the year, we'll look a lot more at the next 2, and that is taking the log, or a logarithm of 0 or a negative number. You probably touched upon logs a little bit. You can never take the log of a negative. That's not a thing. So if that doesn't make sense, we're going to do a lot more logarithms in here. Don't worry. But that's one. And then if you have trig functions besides sine and cosine. Trig functions are the second half of this course, so we will deal with a lot of those. But if you have a tangent or a cotangent, or there's a secant or cosecant function, you're going to have domain restrictions because there's going to be vertical asymptotes. All these things also, right, in this case you'll get a vertical asymptote. Here you're getting a vertical asymptote. Here you're getting a vertical asymptote. If you get a negative under an even root, you just get like a square root on its side, and it just stops it, and like where the vertex would be. So but those are the things we're going to look at when we want to look at finding domain. I think we'll start probably tomorrow we'll do some examples of this as our warm-up.